Trasmetti dal vivo. Let's go. Okay, I think we are live right now.
Not yet. I don't see it already. I wait here that I see it on.
Yes, we are live. I see it.
Yes, now we are live. Yeah. Hello, I warmly welcome you to our 66th webinar by the Academy of Space Renaissance International. On this 8th of July, 2024, I'm really delighted that you have come to join us. My name is Sabine Heinz, and I'm the person responsible for our webinar series and one of the vice presidents of SRI, and also responsible for our art chapter. Our today's special guest is Dr. Ruida Xie, and he will talk about the mission designs for asteroid mining. Welcome, Dr. Xie.
Thank you, Sabina.
Yes. And I also would like to welcome Professor Bernhard Foing. He's our president, and he is right now in Tokyo. Hello, Bernhard.
Yes, indeed. Space Renaissance is on a migration tour in Asia now, where I was last week in Nanjing University for a series of events, including an open summer school, but also we started a new laboratory that is partner with Space Renaissance and also partners with the Lunar Exploration Society, where we are going to do some joint research. Now I'm in Tokyo in a space-type summit where I could meet a number of very good colleagues from all over the world and that are investing in activities with Japan. And next week, we should be going to COSPA at the Committee for Space Research, where we'll have thousands of space researchers presenting their work. And we'll be also organizing some session on lunar exploration and Mars exploration. So it's very hot here, I have to say. In this part of the world, we found some extreme, not as extreme as the moon, but still extreme hot temperature. But yes, we are looking forward to hear more about exploiting resources, asteroid mining. So I'm looking forward to the next lecture. So best wishes from Tokyo. You can see a bit of Tokyo in the background.
Sounds so interesting, Bernhard. How many degrees do you have actually?
So now it's a night time because it's 10 o'clock at night, but during the day we reach some 34, 35 degrees.
It's hot. It's really hot. Yes. Yeah. And I have another question. Do you speak Mandarin?
No, but we have to start now to learn because China is so active, and so it will be an important player in the future Moon Village, but also in the future Space Renaissance.
It is
and they have 1 billion
player.
people so to contribute.
Already.
Many creative minds.
Yes, I know. Thank you, Bernhard. And I also would like to welcome Adriano Ortino. He is also a vice president and a former president of Space Renaissance International, and one of the founders of SRI. Hello, Adriano.
Thank you very much, Sabine, and welcome everybody. Welcome Ruida Xie, and welcome Bernhard. And Sabine, our fantastic conductor of these webinars, is always very perfect in her doing. Yeah, I have some exciting news too. Very briefly, it is related to the Space 18 SDG proposal, our proposal to add an 18 SDG to the 2030 United Nations agenda. And I can say that after our presentations and speeches at COPOS, there is a rising interest around this proposal. We have probably some countries, some UN state members from Africa that are interested maybe to endorse our proposal and to officially present it to the UN General Assembly. And so we have several talks in this week and the next week that could lead to important developments on this side. And we are also working to participate to the Summit of the Future of the United Nations ECOSOC in September. And so we are working a lot, and there is no holiday for us in this summer. But yeah, I think it's good because space have to go to space, and space for all. Okay.
Thank you. You are very, very active, and you are doing a lot of amazing work. Thank you for this. And okay, you may not have vacation, but you are traveling around all around over the world. So this is something nice too. Dr. Xie, before I give you the floor, I would like to introduce you to our audience. I also would like to welcome our audience. And if you have any questions, please write it in the chat. I will forward them to Dr. Xie after the talk. Dr. Ruida Xie has a PhD from the University of New South Wales. He has conducted his research at Australian Centre for Space Engineering Research for the past few years. He designed space mining missions on the Moon, asteroids, and beyond. His research interests includes off-Earth mining and space resource utilization, mission design, and trajectory optimization. Particularly, he is interested in the application of artificial intelligence and big data in space sector. His past research experience includes the design of attitude control system and task planning for remote sensing satellites, etc. In 2023, he was granted the Emerging Space Lasers Award of the IAF. Congratulations. And he is a reviewer of Acta Astronautica Advances in Space Research. Dr. Xie, the stage is yours.
All right, thank you, Sabina. Let me share my screen. Okay, just to confirm, is it in full screen now?
Yes, perfect.
Okay, thanks for the introduction. Let's begin. So some background here. Asteroid mining, for some more precise official definition of it, it is the hypothetical extraction of materials such as water, metal, from the asteroids or other minor planets, including the near-Earth objects. So, but I know what I've been told, or what you may have heard, either from social media or from private company propaganda, that asteroid mining is the next gold rush in space. So is it true? Have you ever considered how to make money from the space mining? Well, some of the results from the research will give you some more information about the answer to this question, and some results may be different from your intuition. So let's get started. The asteroid mining is actually not a new concept. It is, in fact, quite old. It has been discussed since the last century. And let me get my pointer. So this guy, the Konstantin Tsiolkovsky, who developed the famous rocket equation, he had some thoughts about asteroid mining in 1903. So that's over 100 years ago. But at that time, due to the limitations of technologies, these ideas are more like science fictions rather than serious projects. So I would say only until recent years, asteroid mining are becoming technological and financially feasible. In 2010, there are many startup companies like Planetary Resources, iSpace. Some of the companies still survives. And in 2017, we have the famous asteroid redirect mission from NASA, although the mission has been suspended, but we have seen the potential of asteroid mining. And in 2022, NASA started to produce oxygens in space. And in the same year, the Japan Aerospace Agency, they found water in Ryugu. And in 2023 and beyond, it's the stage for moon exploration, like NASA, like ESA, like China, India, they all have their own plans. So this is the very quick look of the space mining or asteroid mining history. So why asteroid mining? I think there are two purposes. One is the space exploration, the spaceborne material to be used in space to reduce the cost. As we all know, to launch anything from Earth's surface would be very expensive. Even use the most efficient launch vehicles like Falcon or Falcon Heavy. And the second is the it's like the supplement for the terrestrial resource. It's a planned potential solution for securing the supply. But in fact, in this study, we found it's really any resources you extract, you retrieved from space, they cannot compete with the terrestrial price of the terrestrial resources. Let's talk about it later. So what do we want from these space rocks? There are waters, there are precious metals, there are common metals that can be used for life support and manufacturing, and it is quite important for the future, like moon exploration or even Elon Musk's Mars exploration. This also brings why we want to perform this study. So asteroid mining missions need to be carefully designed. As you can see, it's not a common scientific space mission. It's more like an economic activity. So it needs to be carefully designed, or otherwise it can hardly be profitable. This is also the motivation of this study. We need to tell the investors or decision makers or even governments which asteroid to mine and when to mine and how to retrieve those resources and how much money the space mining industry can make. So these are the questions we want to answer in this webinar. Let's directly go to the part one, which to mine. And this is the question of target selection. So there are so many targets to choose, and the number is still growing. New asteroids are found on a daily basis. So when I started this work, there were only about 20,000 near-Earth asteroids recorded in the NASA's, in the JPL's small body database. But now the number has grown to 30,000 and is still growing fast. This is because we have more powerful telescopes and we are able to find smaller and darker objects in space. So this is actually a good thing because darker asteroids, they are probably C-type asteroid, which may contain water, which is the most desirable resource from space at the moment. And because we have so many targets here, and it is really hard to compare the mineability of those targets. So different studies, they have different time frames, they have different mission architectures, they have different trajectory design method or dynamical models. They have different spacecraft configurations, assumptions, they have different evaluation metrics. So we need to like build up a standard or perform a comprehensive study to evaluate the mineability of the entire near-Earth asteroid population before we can say which one is good, which one is not that good to mine. And what we do is mainly these four things. We perform a round-trip accessibility analysis for the entire near-Earth object population. And we combine the round-trip accessibility analysis with the asteroid taxonomy investigation. This asteroid taxonomy basically tells you what type of resources can be found on a particular asteroid with particular spectral type. And we created the accessible resource maps, and we constructed figures of merits based on the multi-return mining mission architecture. And we finally rank those near-Earth objects based on their mineability. And let's have a closer look of how we achieve this. First is the dynamics. This is the basic of all space missions. So these missions are designed using the so-called patched conic method, which breaks the entire mission into a sequence of distinct phases, where each phase is a separate two-body problem. So this assumption simplified the entire mission architecture. The missions consist of 4 phases. So the spacecraft will depart from Earth parking orbit, rendezvous with the asteroid, and perform the mission and transfer back to Earth to an highly elliptical orbit. We set the highly elliptical orbit because we know we want to reduce the capture velocity change to save the energy. That is to save the cost of the mission. And the spacecraft will do the aero braking at the apogee. Every time it passes the atmosphere, it will reduce its speed, and it will have a smaller apogee radius until it reach the 400 kilometers height. Then it will do another maneuver to enter into the parking orbit and wait for the next mission. So for each single mission, we have a closed loop. Here's an animation illustration. The spacecraft will have velocity changes upon the Earth departure, the asteroid arrival, the asteroid departure, and the Earth arrival. So both inbound and outbound trajectories are computed based on the two-impulse model, and there's no midterm maneuvers considered here. And second is round-trip trajectory database, and this is like the foundation of this work, because the asteroid mission planning, you plan the trajectories from and to that asteroid. So the trajectory database is constructed using the so-called the grid search method. That is also the exhaustive search method for each Earth departure date, we search for different outbound time of flight, and we have different asteroid arrival date. And for each asteroid arrival date, we try different asteroid stay time, and we obtain different asteroid departure date. And for each asteroid departure date, we try different inbound time of flight, and we obtain different Earth arrival date. So each round-trip trajectory can be represented by a series of these time or dates. And we store the data like this. We store the departure date, outbound time of flight, stay time, inbound time of flight, and the delta V consumption in different stages of this round-trip mission. And here is the overview of the database. Here are the parameters we use for the search. This search were performed in parallel on the high-performance computing system, and the process time is about 318 core hours. We stored 8 million round trips, and this is just a coarse search because the time step for search is 20 days. So if you want to get more precise results, you may, adjust, refine the search steps. So after obtaining the database, we may create the accessible resource map. So asteroids, they really have very diverse compositions, but assuming the surface and internal composition are similar for those small bodies, then we can use the asteroid spectral type to determine the composition of an asteroid. And this is also a very commonly used assumption in the field of asteroid mining. And there are many taxonomy systems, but basically the resource types can be categorized into 3 groups. That is C group, X group, and S group. And of course, there are a lot of subtypes that can provide useful information, but it is really beyond the scope of this work. So we've just discussed the big group of those resources. And this is the something we call resource map, the bubbles. So each bubble represents an asteroid, and the bubble size represents the equivalent diameters of those small targets. And the color indicates the estimated mass of these targets, because different asteroids, they have different subtypes, and different subtypes, they really have very different densities. So a larger bubble doesn't mean it really have a large mass. So the X group asteroid may contain precious metals like platinum group metals. And we have C group targets resource map. There are hydrated carbonaceous contracts, so we may find water on them, and this has been approved by the Rugu mission. And we have S group targets. They are linked to the ordinary contracts, and they are most commonly observed asteroid in space. Maybe 40% or more near-Earth asteroids are S group asteroids. So they are silicates rich, and they may also contain water or metal, but they have a very low concentration. And these maps can be like a guidebook for the mission designers to select their targets. Then we have a look at the mission architecture and the mission design process. The mission architecture we use is the one main manned mission plus the in-transportation mission. So there will be one main mission to transport all necessary equipment from Earth to asteroid. And the spacecraft with the mining equipment will stay on asteroid for a very long time until the end of this mining mission. And during this time, there will be multiple transportation missions. So the transportation missions will arrive asteroid at a certain time point to collect the resources, to process the resources and bring the resources back to Earth. So there will be some scenarios where the transportation missions even started before the main mission, because they really need an energy efficient or delta V efficient trajectory. So they may need longer time for the traveling. So using this mission architecture, we may use two methods to design these missions. One is called, we call the approximation method. That is, during the asteroid mining time, we set a number of resource collection points, and for each resource collection time points, we search for available mission opportunities. We find a trajectory that can transport those resources back to Earth. So this is only approximation method, but it's fast, but it has a very low fidelity, because sometimes if you alter this time point a little bit earlier or a little bit after the previous one, you may have a more optimized results. And the second one is the full optimization method. We didn't use it here, but we use it in the more detailed plan. I'll introduce this later. So by using the first option, we may design some multi-return missions to estimate how many resources we can collect from the asteroid, and we can estimate how efficiently we can collect those resources from the asteroid. And we construct some figures of merits to evaluate those asteroids. The figures of merits we used are here. First is the minimum round trip delta V and the number of available trajectories. These two metrics indicate the resource accessibility. The second one is the total delta V consumption assumption and the propellant consumption. These are represent the cost of the asteroid mining missions. And the third one is retrievable mass or profitable mass and propellant cost efficiency, we call RRP. This indicates for 1 unit of propellant, how much resource mass the spacecraft can bring back to Earth orbit. So these are the metrics to represent the actual returns from those from the asteroid mining mission. So we use those figures of merits by plot those line plots. So we design multi-return missions under different delta V per mission limits. We visualized the figures of merits using these line plots and examine the mineability. Sometimes if we set our delta V budget to a very low level, for example, to 7 kilometers per second, then we found the asteroid 2000 EV5 is not a good target because the profitable mass is only about 100 tons. But if we increase our budget to maybe to 9 or 10 or 11 kilometers per second, we found the asteroid could provide over 400 tons of profitable mass. So we cannot determine the mineability using a single delta V limits. We need to plot those line plots to comprehensively evaluate the mineability of these targets. So some interesting results. here. Okay, those tables doesn't look interesting. So we just give you the top 20 precious metals mining targets based on their minabilities. Here is the minimum delta-V consumption. Here's the number of trajectories. Here's the maximum, minimum, and median RP. This indicate how efficiently we can transport our resources. And this is the resource return mass. This is the total delta-V. And these are the top 20 water mining targets. And especially we consider the comets. We found 15 nearest comets are mineable, but they're less attractive than the current known water-bearing targets. The maximum profitable mass is about 200 tons. This is equivalent to the asteroid target ranked 43. So these nearest comets are mineable, but we really not suggest not to go there. And top 20 silicates mining target. Before that, I want to show you some interesting fact, is that we observed from silicates mining target, the larger target you choose, the higher that you may have to pay. So as you can see, for S-group asteroid with diameters larger than 500 meters, they usually have a minimum delta-V cost of over 8 kilometers per second. So so we may need to decide to choose a smaller asteroid or or we have to pay a high delta-V consumption. Here are the top 20 silicates mining targets with diameters lower than 100 meters and larger than 100 meters. And for the unclassified asteroid, actually most of the accessible nearest asteroids are unclassified. So we assume they're water-bearing or non-water-bearing, and these are the feasible target, no matter they are water-bearing or non-water-bearing. So there are very promising targets for mining regardless of their resource types. So they're worthy of more consideration for future prospecting missions. And let's have a look at some summaries of this part of the work. We found about 46% of nearest asteroid are round-trip accessible. We found millions of tons of resource mass accessible, but even if we consider maybe 10% of concentration level, the quantity is still very considerable. And we listed the top 20 targets for water mining, precious metals mining, and silicates mining. And we also gave 20 unclassified asteroid for future prospecting missions, regardless of the resource types that they may have. And about comets, we found they are not ideal for water mining because the profitable mass is less, and you have to pay longer time and a higher delta-V's to reach them. And regarding the mineability, we found that accessibility doesn't mean mineability. Accessible with higher delta-V may have much higher profitable mass. And we also found that the ISPP. ISPP here is the in-situ propellant production. That means the spacecraft can produce the propellant it needs for the return trip, for the resource transportation return trip. It will save 60% to 90% of the propellant. And it is very critical for future mining mission. And none of the currently known water-bearing targets are profitable unless using the in-situ propellant production. And we also found that more energy-efficient transportation methods should be considered, like low-thrust transfer, which will be introduced in the next session of this webinar. Because most of the propellant are used, most of the resources of propellant are used during the transportation trips. And about the asteroid sizes, we found the smaller targets are usually more accessible, and they can achieve higher retrievable mass with higher transportation efficiency. So mission designers may have to choose targets with proper size according to the time frame and expected yields, rather than always choosing the ones with larger reserve, because you have to pay much higher delta-V. You may have to pay a higher delta-V. So some summary of future work. Let's skip this part and go into part 2, how to retrieve. So we have introduced where to go, and the second part we will focus on how to retrieve those resources. Only the resource we can retrieve at a relatively low cost are favorable. Otherwise, even if there's a big asteroid with gold, the cost to retrieve it could be higher than the product value. So the retrieve process is actually the resource transportation problem. This can be a time-consuming and difficult task when using the time-dependent trajectories to design those missions, especially when we use the low-thrust propulsion. Let's have a look at the propulsion options. So generally, we have two types of propulsion options. One is the chemical propulsion, which results in the impulsive trajectory. The other one is the low-thrust propulsion, which will result in the low-thrust trajectory. For impulsive trajectories, it refers to a trajectory that is affected by impulsive forces. To simplify, so it assumed that the thrust to mass ratio is sufficiently high, so firing a high thrust chemical rocket will change the velocity instantaneously with no change in the position of the spacecraft. So the interplanetary impulsive transfers between the Earth of an asteroid target can be constructed by solving the Lambert problem. The Lambert problem is to determine the transfer trajectory that connects the two position vector R1 and R2 with respect to the central body, that is the Sun in this case. The advantage is that there is plenty of method to solve the Lambert problem, and it can be solved efficiently. And it is the most commonly used method for preliminary mission analysis. But it really has a very low fidelity because some of the delta V's or some of the impulsive trajectories can never be achieved in practical. So the second option is the low thrust trajectory. Compared to the impulsive propulsion, it's the low thrust propulsion or low thrust trajectory is a very different one. In this propulsion method, the charged particles or plasmas are accelerated using the electromagnetic forces and ejected at very high exhausted velocities. So the thrust magnitudes of low thrust propulsion are very, very low, probably 200 to 500 micronewtons. But the engine can operate for a very long time to accumulate the delta V's required to reach its destination. The low thrust propulsion really are really efficient. It can save a lot of propellant, but the difficulty is that design such trajectories is very, at least it's much more complex than solving a Lambert problem. And this also brings why we need this study, why we need to study the design of a low thrust trajectory. Because we don't know the capability of different low thrust propulsion systems with different power level in the asteroid mining scenario. We've seen a lot of excellent work studying the impulsive missions for the near-Earth asteroid population using the numerical approach, but we haven't seen any work investigating the low thrust propulsion, low thrust trajectory regarding the near-Earth asteroid missions. This is because the complexity of low thrust optimization process. Optimizing a single low thrust transfer would take several minutes, and we have hundreds of thousands of low thrust transfers to optimize for each asteroid. At the same time, the number of the observed asteroids is growing all the time, so we could not pay the computational effort to continuously optimize new trajectories. What's more, in the mission opportunity search progress, the convergence of the low thrust optimization cannot be guaranteed. That means you may spend a lot of time to optimize a trajectory from Earth to an asteroid, but finally you find the trajectory is actually not feasible. There's no feasible solution. So these challenges makes it almost impossible to use the conventional technique like direct or an indirect optimization approach to solve this problem. So in this work, we use some more advanced deep neural network technique to replace the conventional method to efficiently design the low thrust transportation or supply delivery mission for the asteroid mining missions. I'm going to give some background regarding the low thrust trajectory design here. There are basically two categories of method, like I said before. One is the traditional method, including direct or indirect optimization. And the traditional method basically convert the entire optimization problem into an optimal control problem. For example, this Sims-Flanagan transcription is one of the most efficient among the traditional method. So it discretized the entire trajectory into some eco-time segments with bounded impulse applied at the segment centers as control points. We have some constraints, for example, the thrust magnitude or the continuity of the state at the match point. And we have some variables, for example, the initial mass, the thrust direction and magnitude. So this is a nonlinear programming problem, and solving it is very time consuming. As I mentioned before, we even don't know whether or not the optimizer could find a feasible solution that satisfy all the constraints. So so we use the alternative method based on the deep learning technique. So it extracts the features from the mission configurations, such as the spacecraft configurations, ephemeris, and is sent to the deep neural networks. And the disadvantage of this method is that it cannot provide the detailed thrust profiles, but the transfer cost is a cost estimation is all we need. So this is the framework we constructed. We just replaced the conventional method using a deep neural network classifier and a deep neural DNN regressor. This DNN classifier is to predict the feasibility of low thrust transfer. The inputs are the initial mass of the spacecraft, the asteroid ephemeris and mission time frame. The outputs are the labels predicting the feasibility of the input transfers. If a transfer is feasible, then it will be sent to the DNN regressor, and the DNN regressor will tell you what is the propellant consumption or what is the minimum time consumption of this trajectory may use. And we have a DNN classifier has a prediction accuracy of approximately 98%, and the regressor has a mean relative prediction error less than 1%. So this is actually can completely replace the conventional method. This is the prediction error of like acceptable as at least in my experimental work, it works. So here's a little bit efficiency comparison. We used 100,000 low thrust trajectories to test the efficiency of two methods. The traditional method used to 2-segment the Sims-Flanagan transcription, and it would take about 336 core hours. But the DNN models only take about 1 minute. So there's a huge efficiency improvements. And we can use it to design some real world trajectories. So the low thrust propulsion can be achieved by many power sources like nuclear or solar electric propulsion. Currently, the most promising method is SEP. So we can use the models we just developed as surrogate models to design the low thrust trajectories with different solar electric propulsion power levels. We extract the parameters from literatures like these. We construct 6 kilowatts, 150 kilowatts, 300 kilowatts, and 500 kilowatts SEP spacecraft with different initial mass, ISPs, thrust magnitude, at and together with the deep neural network method adjusting.
This is only the autopilot. We don't need recording because we are on YouTube and it will remain on YouTube. So no need to be recorded. Okay.
Okay. I thought it's a time reminder. So, yeah. Where were we? Yes, the SP spacecraft transportation capability. So we use different SP spacecraft configurations to test their transportation or supply delivery capabilities. The mission architecture we use is similar we used before. It's a round-trip mission architecture. The difference is that for the outbound transfer leg and inbound transfer leg, we used the deep neural networks to design low thrust trajectories. And we analyzed the solar electric propulsion capability in different scenarios. And here are some results. So in the supply delivery scenario, the spacecraft with a dry mass of 13,500 kilos using 60 kilowatts SCP is used to deliver 5,000 kilograms to 15,000 kilograms of equipment to near-Earth asteroid and return to Earth. So the results show that in this case, for example, the 60 kilowatts spacecraft can deliver 5 tons of supplies to let's say 40% of the near-Earth asteroid in a round-trip mission. Considering your resupply for consecutive mining missions where the in-situ propellant production are available, there will be additional like 16% of the near-Earth asteroid can be resupplied. And for the resource transportation scenario, we use 150 kilowatts, 300 kilowatts, and 500 kilowatts spacecraft to study their transportation capability. We try different dry mass, we try different initial mass, we try different resource mass from 10 tons to 120 tons to see their capability. In different cases, the accessible near-Earth asteroid numbers are very different. And of course, the accessible resource mass are very different. Let's have a look at the visualization of these results. So we are able to plot resource transportation capability boundaries of different SCP propulsion system. For example, if one mission designer plans to use 150 kilowatts SCP to transport 10 tons of resource from an asteroid, this will be the boundary of the transportation capability. Only asteroid with orbital elements with semi-major axis or eccentricities within this boundary would be feasible target for the transportation task. Using the same method, we may plot the boundaries in different coordinate systems where the horizontal axis or the vertical axis are different orbital elements. And these boundaries are constructed using the polynomial regression method. Here are the parameters and the equations. So let's have some summaries here. So in this part, we established a low thrust, more specifically the solar electric propulsion spacecraft accessible boundaries, and we construct a low thrust round trip trajectory database that contains over almost 28 billion round trip trajectories, and we evaluate the near Earth asteroids mass transportation capabilities of different solar electric propulsion systems. And I think mission designers will benefit from the constructed DNN models and the low thrust mission opportunity search algorithms. They can always use these models to construct their own mission designs. So this is part two, how we retrieve those resources. It's probably maybe a little bit boring, but it's really necessary for the next one, the mission design part. So that answers the question when to mine. So why this study? Because people have been studying the asteroid mining or lunar mining for many decades, and they have found that space mining is an economic activity. So pre-feasibility study is very necessary prior to any investments. So when we want to design the large-scale mining campaigns, we need to design a bunch of missions performed by one or multiple spacecraft to explore or mine on one or multiple targets and finally deliver the products to customers or space depots or other space locations. For example, maybe the lunar outpost and other locations. So asteroid mining campaign designer must consider different aspects of the space mining mission. They need to make decisions on the overall strategy, supported by the mission level details or trajectory level details we introduced before, and they need to consider the mission architecture, they need to consider the space launch vehicle performance, they need to consider the cost, the economic performances. So it is quite complicated, and we need to construct a methodology to consider all these factors in our mission designs. So we present you the campaign design framework here. Here's the framework overview. It can be used as a standardized workflow to design space mining campaigns for different off-Earth mining scenarios, such as lunar mining or asteroid mining or Mars mining. But here we only introduce how we design the asteroid mining. So we can use it to estimate the profit that can be made from mining activities. We can analyze the resources needed, time needed to perform a specific mining mission, and the modules in this framework have clear interfaces, so they can be exchanged, replaced for different purposes and fidelity levels. I'm going to briefly introduce the key modules of this framework. So the ephemeris generation modules, it is used to, of course, it is used to generate ephemeris for different asteroids, but it has two modes. One is we use the Keplerian propagation. It is fast, but really has a low fidelity. And we can also use the SPK formatted data from the horizon. And we can use the SPICE toolkit to read and process those data. It is relatively slower, but it has a higher fidelity because it considers the perturbations and uncertainties. And second is the asteroid taxonomy and physical parameters module. It determines the asteroid resource types and the reserve. For example, if an asteroid is C-type, like I introduced before, then water ice or hydrated minerals are assumed to be on that asteroid. Or if an asteroid's spin rate is too high, you have to have additional designs or additional mechanisms to despin that asteroid before you can mine it. That means additional cost. And then we have this cost parameters module. It provides the cost value for economic model. These values can either be estimated by some models, and as I have learned, NASA has some open source models like quick cost models. You can design your own spacecraft and you can estimate how your spacecraft may cost. Or they can be directly obtained from space companies' brochures or websites. Like if you want to know how much they're going to use to design or build a Falcon launcher, then you can always find them on the SpaceX website. So this to obtain those parameters is not a problem at all. And there are 4 basic models. The dynamic models provide the dynamical details for interplanetary or cislunar transfers. The mission architecture determination is to predefine the passes between the target, the customers, the space depots, and it outputs the supply option, mining option, transportation options to other modules. The linearization and mining model, it is used to discretize the nonlinear problem into a linear one, and together with this economic model, to provide the input for the final campaign design. And there are three algorithm modules, including trajectory generation module, the mission opportunity search module, and the campaign design module. These two we have introduced them before. So next part, I'm going to give a closer look of how we design long-term mining campaigns. The design process is as follows. After we have used the grid search method to obtain the trajectories to establish the trajectory database, we can plot figures like this. So impulsive transfers is measured by the delta V, and the low thrust transfer cost is measured by the mass fraction. And this figure, we really called it a pork chop plot. It visualized the transfer cost as a function of the mission opportunities. So each point on this plot, it represents a round trip, and the color indicate the transfer cost level. And after this, we can use such a figure or such a data set to select the desired itineraries. Here we can start a campaign design using the mixed integer programming. If you have a continuous variable, we can always use the mixed integer programming or the other methods in this module. And the objective of the campaign planning is to maximize the overall profit or the net present value. That's the profit counting the time value of money. And this transparent block here is the campaign design window. So all the missions must be within this window. We can try different length of this window, and we can move this window along the time axis, design campaigns with different start time and duration, and see what we can find using this sliding window. And this is an illustration of mining campaign design for asteroid Bennu. That's the target for Osiris Rex. Yeah, here we initialize a 20-year mining campaign. So this window started to move from time 2030. And this figure here shows the discretized available mission opportunities within this campaign period. The right plot here is the scheduled and optimized campaign. And the left one consists of horizontal bars just like this one. There's just too many of the bars, so they look a little bit different. So each bar here represents a timeline of a mission. Different colors represent different stages. The navy blue is the wait time before the mission starts, and the orange ones is the outbound flight time. The yellow ones is the stay time before mining. The purple one is the mining time, and the green one is the stay time after mining. This is because you can see spacecraft usually need to wait for a very long time, even after the mining activity. This is because when we use impulsive trajectories, the spacecraft will have to wait for a very long time to find a energy efficient or delta V efficient trajectory to transport the resource back to Earth. Otherwise, it would be too costly. And we can move the campaign design window like this. Oh, before the illustration, we want to show you some interesting fact between interesting comparison between the impulsive mining campaign and the low thrust mining campaign. As you can see, even like I said before, for the impulsive ones, the spacecraft they will have to wait for a very long time after the mining activity and before the return trip. But for the low thrust ones, it's very different because all trajectories are very energy efficient. In this case, the time matters more because the longer you take, the less net present value you will get. The sooner they get back to Earth and sell the product, the higher net present values they can achieve. So as you can see, the spacecraft transfer back to Earth as soon as they complete their mining mission. And this is the illustration of the campaign design process. As we move in this window, we can see we have different available campaign trajectory opportunities, and we have different campaign designs. And after that, we can obtain a figure like this. This is the statistical results of the cost, revenue, and profit during the year 2030 to 2050. We can see three peaks. Peak period in the profit plot, we call it mining seasons. These are the feasible years to start a mining campaign. So the most profitable campaign should start at 2047. The total profit is about $1,200 million. And this campaign requires 10 spacecraft and 21 flights. This is only an example of the campaign design. And the framework can also be used for sensitivity analysis. We can also accounting different parameters, spacecraft parameters. The input parameters is changed one at a time, and we can observe the effect of that changed parameters on cost or revenue or profit. So by using this method, we can identify the parameters that is most critical for a successful mining campaign. As you can see, this sensitivity analysis is quite different from a commonly seen one, because the start time of the asteroid mining campaign also matters. So it is used as one of the dimensions of this sensitivity analysis. What we have found is that among the spacecraft related parameters, the spacecraft capacity matters the most. Then is the dry mass, and then is the mining rate. This is at least this is very different from my intuition. As I thought before, the mining rate is the most important factor that would influence the mining campaign. And we can also determine the sensitivity to some economic factors. We found that the selling price and launch cost have the greatest impact on the net present value. And the operation cost, the production cost, and the maintenance cost have very limited impacts on net present value. This is based on the assumption that the size of the mining industry has reached a certain level. For example, you arranged 100 and more spacecraft in the campaign, so each spacecraft will have a very low, not very low, a relatively low production or manufacturing cost. And regarding the asteroid mining seasons, we also find some interesting facts. We categorized the mining seasons into three groups. The type 1, we named it type 1. So targets are suitable for mining all the time, and they do not have a noticeable mining season. This is because this is mostly the mining season is because the asteroid's periodic close approach to Earth. But in this case, we focus more on the economic patterns that we can learn from these targets. So for these types of targets with type 1 mining seasons are very favorable, because basically you can mine anytime you want, at least between 2030 to 2050. And we have type 2 mining seasons. So targets will have noticeable mining seasons, and each mining season may last one or several years. Thus, we may find 3 or 4 mining seasons in the observation window. And the targets of this type might be further categorized into 3 subtypes. First of all, the targets like 2014 FA7, they have short mining seasons. The peak net present value only lasts for 1 or 2 years before dropping sharply. Second, target like Bennu or 1989 UQ, they have relatively longer mining seasons, probably 3 to 4 years before significantly drop. Third one is drop on net present value. And the third one is targets like 1989 ML. They have much longer mining seasons, probably 5 to 6 years. So there are regardless of their subtypes, the type 2 targets are favorable targets. But the mission designers or the companies should really pay attention to their campaign, Asteroid campaign start year. Otherwise, it will get a relatively low economic return. And the type 3 targets have noticeable mining season, but interval between seasons is very long. As you can see, in some of the cases, we can only see a single trend of NPV. That indicates we only observe the partial of the mining seasons. So mining on the type 3 targets require the mining companies to seize the opportunity for mining during their mining season. Otherwise, they may need to wait for a very long time, probably over 20 years, before the next season showed up again. And lastly, we may picture the asteroid mining industry using a larger scale of campaign designs. Here we're gonna make a 35-year mining plan. The design process following the same process illustrated before. So for each target, the difference is that instead of designing the missions, the campaigns on a single target, we designed the mining missions on all the classified C group asteroid that may contain water. So the design process is exactly the same as I illustrated before. For each target, we constructed the round-trip missions, and we optimized the campaigns, and we combined the mission scheduling of all the water-bearing targets, and we created a resource pipeline. And we can obtain the flows of net present values, revenues, and profit and the cost. So as you can see, mining on multiple targets will form a resource flow that may fill the gap between the mining seasons. So we may have a steady resource income for a very long time. So in this case, we use the 500 kilowatts SCP spacecraft. This case is also the most profitable among the cases shown in this table. The profit over the period of 2014 to 2057 is around $400 billion. The maximum delivery frequency is about 600 times a year, and average delivered mass is around 91 tons per mission. And this is the details of the 35-year plan. So for each year, we listed the top 6 targets that contributes the most to the yearly profit, and we can see if in different years we have different targets that contributes the most to that year's profit. And here's some summary of this part. So we present a framework, and it is considered as a systematic solution for near-Earth asteroid mining campaign design. And we have illustrated the use of the framework in the campaign feasibility study, the sensitivity analysis, the mining season determination, and large-scale mining campaign planning. And we have considered the realistic trajectories, especially we used the deep neural network-based techniques to construct the solar electric propulsion-based low-threat trajectories. And I think this part of work provides mission designers with a very useful tool to design campaigns with greater fidelity and flexibility. And lastly, some facts of this work. We found that the current known targets could form a 21,000 billion precious metals mining and a 13,000 billion water mining industry. So the size of this industry is very considerable, and we should always increase the scale of asteroid mining. So as I mentioned before, the number of the manufactured mining spacecraft if the number is too less, then we will have a relatively high cost on maintenance cost or manufacturing cost. That would make the entire campaign less likely to be profitable. So we should always increase the scale of the asteroid mining campaign. Otherwise, for smaller scale, for example, for a smaller scale mining industry with about, for example, 20 spacecraft or 30 spacecraft, the net present value can rarely be positive, and the maintenance cost will be really high. And that's the thing I wanna say next. So for long-term mining missions, the maintenance cost is very critical to the success of the mining campaign. So it is suggested that redundancy should always be considered in the spacecraft subsystem design. Regular in-space, low-cost maintenance techniques should be further developed, because our mining missions usually last 20 or 30 years. So if you have a very strong spacecraft, then you are more likely to be profitable. And we found, and always use solar electric propulsion. It can increase the profit by 2.8 to 8.7 times. This is also a discovery in our sensitivity analysis. So when using the impulsive trajectory, when you tuning those parameters, sometimes you will never find a profitable case. But when you use the solar electric propulsion-based low-thrust trajectories to design campaigns, and you tune those critical parameters, you will find that it will only influence the economic return, but the campaign always returns positive net present values. So the SCP is really a game changer in future space mining missions. And I think that is all I'm going to share today.
Yeah, thank you very much for this very interesting lecture. Could you stop sharing the screen so we are all be seen? Yeah, perfect.
Yeah.
I have a question from the chat. Boris Petrovich is asking, please suggest some open source software that can be used to simulate asteroid mission orbits and example spacecraft trajectories.
Yeah. Yes, I understand this question. So there are actually a lot of softwares from NASA or GitHub you can find to design trajectories. But if you want to, accelerate your design process and construct the database I used in this work, you have to, write in Python or Java or MATLAB by yourself. But regarding the open source software, you can also use the GMAT. That's a tool from GPL. And there's PyCap. That's a Python library developed by Daryl Iso from the European Space Agency. It's a very good tool to design the impulsive or low-thrust transfers. And also there are some EMTG, the evolutionary trajectory designing tool. I think it is developed by the Jacob England. It can be used to develop more complex gravity assist missions in your asteroid mining design. But like I said, it only supports small scale of the trajectory design scenario.
Thank you. I think he is quite content with this answer, because he said thank you too. Bernard, you also had some questions, I guess.
I have a little comment, because actually I almost traveled to one of your targets, 1989 ML. If you want to know, at the beginning of the story, when we define possible target for SMART-1, the demonstration for solid propulsion, we had some option to go to asteroid and option to go to the moon. And we picked a number of asteroid targets, and one of them was 1989 ML, and there was also a kind of possibly a Kato comet, a dead comet.
Yes.
We've seen Wilson or Harrington, I remember. But 1989 ML was one because it's one of the objects that requires a minimum amount of fuel to go. And using electric propulsion, it was a big advantage. So, but at the end, we decided that it was more powerful to demonstrate electric propulsion going to the moon. And so we did that for you for the future. Now I have a question about just the overall exercise. So clearly you have demonstrated you use a very sophisticated tool to travel there and so on. And the scenario is, okay, you want to limit also the time of stay on the asteroid. But in the long term, isn't it also a scenario where we would send people that would stay long periods? Because if I said, if you want to expand into space, we could leave also some astronaut in a longer duration, and then you would start having a part of our humanity there, like we will have on the moon, we'll have on asteroids. So for this long duration stay, do you have some candidate that you think would be we could recommend for our astronaut to stay for several years?
You mean on an asteroid?
Yes, like the book from Saint-Exupéry,
Little Prince.
Le Petit
I
Prince.
had the same vision. Will you stay for a long term on this small asteroid?
So, what would it take to live to establish a colony on an asteroid?
As a matter of fact, I really haven't considered that problem, because all my designs are based on robotic missions. I have seen that they're sending astronaut to asteroid, but I believe the target there's a limited number of asteroid. You cannot, for example, you're sending astronaut to asteroid to a small tiny asteroid like maybe 100 diameters, and the resource could be depleted in like 10 years or 6 years, because you pay a lot of energies, pay a lot of money to send an asteroid there, and you have to abandon the, let's say, asteroid base in 10 years. That's not economically feasible. So,
but still, it's more like 100 meters is still big. It's a lot of soil. You could grow plants and so on to feed a large community, and it's more material than vacuum of space. So 100 meters, it would be like 1 million ton of material. So still a lot. And there have been also projects where you could also build the foundation, live in the subsurface of the asteroid, transform it in a living place. But clearly, also you use solar electric propulsion to bring some of the cargo material you need, maybe some of the machinery, some of the industry, and then you can do the mining over a much longer period if you have also to sustain at the same time a human community.
But would it be possible to add a question to this, to take something like a net or whatever, because some asteroids are not so big, and to take it near to Earth
and bring it along.
Yes, I think what Sabine said is I've already seen some designs like you said, like your concept is like there's a flexible big net to transport. Yes, I've seen some design, but that's just like the mission concept of the asteroid redirect mission. That plan was original. Yes, originally to bring
the other advanced scenario is you bring a kind of factory that can extract the most valuable, and then so if you have enough time, for that, you bring back the titanium, you bring back some of the rare earth elements,
Yeah.
then you don't need to bring so much material
Yes,
back to
yes.
Earth.
I think that's the most problem of that plan. You wasted too much energy transporting waste materials from
Yeah.
far away to the cislunar space, and it's too risky. For example, if your extraction method goes to the wrong way, there will be an asteroid disaster. Maybe, you know.
Then I had a more catastrophic scenario, as if there would be also to deflect enough, for instance, some of the small asteroids, for instance, to bring it on a collision course with the moon. And you could bring all these resources on the surface of the moon, and then you can mine them in a long period later.
Yes.
Did you identify a target that could be deflected and sent to the moon?
I think moon is natural defender of Earth. I've ever read one of the theories saying why the moon surface contains so many resources that is not supposed to be there, because it like attracted so many small asteroids in the long history of solar system, even before human beings have intelligence.
Right.
So that's why there's abundant resources on the moon's surface. But deep in the moon, what's there? It's still undetermined. So I think it's a good idea to manually to lead some high risk targets to moon gravity.
So let's do some studies, and we will ask you to calculate the orbits.
No, okay.
Thank you so much.
Yeah, I think I can do that. Yeah, thanks for the
thank
question.
You. I will have to leave you soon because of the time.
Yes, I see you are tired.
All the best.
Thank you for joining us, Bernard. It was really nice to have you here, and I wish you a good night and a nice day in Tokyo.
Okay, thank you. Goodbye.
Okay, bye.
Bye. Good luck. Thank you.
Adriano?
Yes. Well, I have too many questions, and I will try to put it simple and make maybe one only big question, if possible.
Yes, maybe, yeah, because I'm.
Well, maybe you know that we at Space Renaissance, we are thinking about the concept of space for all. So we are trying so if one say just a space for all is is a big object, and but interesting questions come when you zoom inside and you start to divide, to make a decomposition in smaller objects. So what does it mean, space for all? We mean, for instance, among other things, that
Is it just me or?
There was an audio blackout. Yeah.
Yeah. Also, it's not only me. You cannot.
I can hear you clearly.
Yes.
It's just a Ruida.
I can hear you, but I cannot see Adriano. Adriano is
aus. I think we lost connection with the asteroid.
We lost connection with Adriano. Yeah. So he mentioned before that he has some problems with the connection, because he is only connected by his iPhone or smartphone. So I think we can stop here. We can wait a minute that he will come back, but if he can't manage it, I would say we close it. And I thank you so much for being here with us. And I also would like to mention to our audience that next week we have also a webinar. I'm just looking who will be the speaker. Just a second. Oops, I have it here somewhere. And the next week talk will be about, oops. Yeah, space exploration, present and future with Walter E. Hammond. And it will be at our usual time at 9 o'clock German or European time, 9 p.m. On the 15th of July. Thank you again, Ruida, for being with us for this interesting lecture. And I wish you all a nice evening, and also Bernard, thank you.
Yeah, thank you.
Thank you.
So I will be at
Thank you.
Cospar time next week, so it will be Korea. So yes, it will be very late, but yes, thank you. All the best.
Thank you so much
Thank
for
you,
joining
Sabine.
us.
Thank you, Bernard.
Bye.
Bye. Bye, everyone.
Hello. I'm sorry because we lost the connection and now we are live again, but I don't know if our guests are still with us or not. We'll try to reconnect everybody. Hello. Hello, can you hear me?
Can you hear me?
Yes, yes, I do. I'm sorry, but as I told in the beginning,
That's no problem. I can hear you.
no, my computer went down of energy, and not my computer, my cell phone went down of energy, therefore the connection was lost. However,
No problem. No problem.
okay, so I try to retake it from where I was interrupted before. Yes, I think that when we talk about benefits from the use of the resources, space resources utilization, we have at least 4 levels. One is the direct resources utilization and commerce, and this that means I don't know if this is the biggest part of the business or not. However, it is an important part of the business.
Yeah.
Then we have the second level is the induced industry, that it will be the space industry on Earth that will grow following this activity of space mining, let's say. The third one is always, even now, is already working, and it is the